Hi everyone. Last time we talked about Gibbs free energy, and today we're going to go over some practice problems so we can see how Gibbs free energy works with different reactions. So we're going to first go over an example from your textbook. In this example, we're going to consider the reaction for the decomposition of carbon tetrachloride gas, so CCl4. And that is decomposing into carbon and chlorine gas. So we have a couple of values here. We have the change in enthalpy for the reaction, and you can see that that is positive. So would that be endothermic or exothermic? All right, so it would be endothermic. So that means that this process requires energy or heat in order to occur. But additionally, because the reaction is drawing in heat, remember that means the surroundings are losing heat. Now, we're also told that the change in entropy is positive. So is the change in entropy spontaneous or non-spontaneous for this system? So it is spontaneous for this system. And that makes sense because we have just 1 mole of reactant and we have 3 total moles of product. So entropy is increasing for the system. However, entropy for the surroundings will decrease because we're pulling heat away from the surroundings. So we're making the surroundings more ordered. And we'll write a little system here next to delta S because that delta S is for just the reaction. Okay, so now A, we're going to calculate delta G at 25 degrees Celsius and determine whether the reaction is spontaneous. So it is a little hard to tell right now if this reaction is spontaneous or non-spontaneous. It is an endothermic process. So it's drawing heat in, and delta S for the system is greater than 0, but delta S for the surroundings is less than 0. And remember, we care about delta S of the universe. So we need to determine the magnitude of delta S of the surroundings versus delta S of the system before we can really estimate if this is spontaneous or non-spontaneous. So what we'll do instead is calculate delta G, and that will tell us whether it's spontaneous. Now in part B, if the reaction is not spontaneous at 25 degrees Celsius, determine at what temperature, if any, the reaction becomes spontaneous. Okay. Now, last time we said that delta G is equal to delta H minus T delta S. Okay. And we also talked about the signs of the delta H and delta S and how that affects delta G. So here, again, we have a positive enthalpy and a positive entropy, but the T delta S overall will be negative because delta S is positive and we have a negative T there in front. So this is going to depend on the temperature, whether this is spontaneous or non-spontaneous. All right, so if delta H is greater than T delta S in magnitude, that means that temperature is low. And then delta G will be overall positive, right? Because delta H is positive, and if its magnitude is greater, then delta G will be positive at low temperature. But then if delta H is less than T delta S, what does that tell us? So that tells us that T delta S is greater in magnitude. It's also negative. So then that would mean delta G is negative. But also if T delta S is greater in magnitude, that means temperature is high. So this would be at high temperature. Okay, so we can make a prediction here that delta G will be spontaneous at high temperature. Okay, so 25 degrees Celsius is around room temperature, so we can maybe predict that that's a pretty low temperature. But let's actually do this calculation to see if our prediction is correct. All right, so we're going to plug in, and I'll use a different color here. So delta H is 95.7 kilojoules, but let's make sure all of our units match up. So delta S is in joules per Kelvin. So let's just multiply delta H here by 1,000 to turn it into joules. And then that'll make the calculation much easier. And then we'll subtract the temperature in Kelvin, but we were given the temperature in degrees Celsius. So let's just do a quick temperature calculation up above. Okay, so 25 plus 273, that is 298. Okay, so we'll plug that in. And then we'll plug in our entropy. Okay, so now if we plug that into our calculator, we should find that the value is 53.3 times 10 to the third joules. So if we're looking at our units, you'll notice Kelvin will cancel, and then everything we made sure was in joules. So our final unit should be joules. Okay, so that means that delta G is positive. If delta G is positive, is that spontaneous or non-spontaneous? So it's non-spontaneous. So this is the opposite of entropy. So remember, delta G also equals negative T delta S of the universe. So if delta S is positive in spontaneous processes, that means that delta G is negative in spontaneous processes. So if delta G is positive, that means it's actually non-spontaneous. So delta S is positive, delta G is negative for spontaneous processes. All right, and that's just a little side note there. Okay, so now we did determine this reaction is not spontaneous, so let's go on to part B. This also matched our prediction. We said that delta G would be positive at low temperatures, or non-spontaneous at low temperatures. All right, so now let's figure out at what temperature the reaction becomes spontaneous. So there's a little trick to this. What we're going to do, let's write out our equation here. So we're going to set everything equal to 0. So delta G is equal to 0. And then we're going to rearrange to solve for temperature. So we're going to use this equality. So if we rearrange, let's say delta H is equal to T delta S. So we just added T delta S to both sides. And then if we rearrange to solve for temperature, temperature is equal to delta H over delta S. And that is the temperature at which the reaction becomes spontaneous. And that kind of makes sense because we're looking at a ratio of the magnitudes of delta H and delta S. So we're trying to see, what temperature will delta H over delta S give us a spontaneous process. Okay, so let's calculate that. So we said that delta H in joules was 95.7 times 10 to the third, and delta S was 142.2 joules per Kelvin. All right, so joules will cancel, and then Kelvin is in the denominator of a denominator, so that will actually be in the numerator when we do our final unit here. All right, so if we plug this into our calculators, we find that the temperature is 673 Kelvin. Okay, so that tells us the reaction is spontaneous above 673 Kelvin. So that's where delta G will start to become negative. So that kind of goes back to why we set delta G equal to 0. If delta G is positive for non-spontaneous processes and negative for spontaneous processes, then we're trying to find that midpoint where delta G goes from positive to negative. So that's why we set delta G equal to 0. And then we solved for temperature. Okay, now this also matches our predictions. We said delta G would be negative for really high temperatures. So that works out. This is a pretty high temperature. Okay, now let's work on worksheet problem 5. So for this problem, we're going to calculate the change in Gibbs free energy for each of the sets of delta H, delta S, and T given in worksheet problem 4. So remember, in worksheet problem 4, we were trying to predict whether or not each reaction was spontaneous, and we were calculating delta S of the universe. But now we're going to calculate Gibbs free energy and see if the reactions are spontaneous or non-spontaneous. Now, if you finished worksheet problem 4 from the other day, you probably already figured out which reactions are spontaneous and which are non-spontaneous. So let's just calculate delta G and double check that we still get the same results in terms of spontaneity. All right, so these are the exact same values from worksheet problem 4. We're just going to plug them into our delta G equation. All right, so again, delta G is equal to delta H minus T delta S. And let's make some predictions here. So we can see that delta H is negative and delta S is negative. And because delta S is negative and it's multiplied by negative T, that means this is overall positive. Okay, so we need to see if the temperature gives us a negative or a positive value for delta G. All right, so if delta H is greater in magnitude than T delta S, that means that delta G will be negative because delta H is negative, it's greater in magnitude. So delta G will be negative for this situation, and temperature will be pretty small because T delta S is small. Okay, and then the opposite is true. So, oh, I already wrote that wrong. Let's flip that. So if delta H is less in magnitude than T delta S, then delta G will be positive because T delta S is positive and it's greater in magnitude. That also means temperature will be pretty high because T delta S is large. All right, so our prediction here is that the reaction will be spontaneous, or delta G will be negative at low temperatures. Okay, and 298 Kelvin is pretty low. Again, it's around room temperature. But let's just make sure that that is the case. So I'm going to make some room here so we can do our calculation. Oh, rewrite that. Okay, so we have negative 95 kilojoules for our change in enthalpy. I'm going to change that into joules just to make it a little bit easier to calculate. So that would be negative 95 times 10 to the third joules. And then we're subtracting 298 Kelvin times negative 157 joules per Kelvin. And here, I'll put a little box around our prediction there. Okay, so now when we calculate this, Kelvin will cancel, we'll be left with joules. But additionally, we should get a value of negative 48.2 times 10 to the third joules. Okay, so delta G is negative for this problem, so that means this is a spontaneous process. And that matches our prediction. Okay, so let's do one more together, and then I'll let you work on C and D on your own. And you can, of course, double check your work on the worksheet key. All right, so B, we have again delta G is equal to delta H minus T delta S. And let's see, we have again a negative enthalpy and a negative entropy, which makes our T delta S positive. Okay, so the same thing applies that we saw earlier. So if delta H is greater than T delta S, that means delta G again will be negative. And temperature will be pretty low for this case, so that would be at low temperature. And then if delta H is less in magnitude than T delta S, we said that delta G would be positive at high temperature. And our temperature for this problem is 855 Kelvin, so that's pretty high. So I'm going to guess that this reaction is non-spontaneous at high temperature. So let's see if that is true. Let's do some calculations here. I'm just going to put a box around our prediction. All right, so delta H, we're going to convert to joules, just so all of our units are the same. And then our temperature is 855 Kelvin. And entropy is negative 157 joules per Kelvin. Okay, so Kelvin will cancel and we'll end up with joules again. And if we plug this into our calculators, we should get 39.2 times 10 to the third joules. All right, so that tells us that delta G is positive at this temperature, which means the reaction is non-spontaneous. And that matches our prediction, so that works out. Okay, so I encourage you to work on parts C and D and try to predict if the reaction will be spontaneous or non-spontaneous. And if you have opposing signs, determine if it will be spontaneous at high temperatures or at low temperatures. Okay, so let's go on to worksheet problem 6. And let's predict the conditions under which each reaction is spontaneous. So we'll try to determine if these reactions are spontaneous at high temperature, at low temperature, at all temperatures, or no temperatures. Okay, so we have 4 reactions here. We'll go over the first 2 together, and then I might have you try the last 2 on your own. And here's the table at the bottom if you need it. So for our first reaction, gaseous water is turning into liquid water. All right, so what we need is the sign of enthalpy and the sign of entropy. So if a gas is turning into a liquid, is that an endothermic process or an exothermic process? So are we losing heat or gaining heat? So if a gas is turning into a liquid, that means that the gas is cooling down. So that means we're losing heat. So this is going to be exothermic. So if this is an exothermic process, is delta H positive or negative? Negative, right? Okay, another way of writing that again is just less than 0. So let's do that. Okay, so now what about entropy? So we can't really look at the moles of reactants and products here because we just have 1 on each side. So instead, let's look at the state of matter. So we have a gas versus a liquid. Which one is more disordered? The gas, right? The gas is more disordered. It has more energy. So that means it has more entropy. The liquid is less disordered or more ordered, so it has less entropy. So if we're going from more entropy to less entropy, is delta S positive or negative? Or is, I guess another way of asking that question is entropy increasing or decreasing? So it's decreasing, right? We're going to a more ordered state, which is the liquid. So delta S is going to be negative because entropy is decreasing. Okay, so that means that we have a negative and a negative. So that refers to row 3. Okay, so delta H is negative, delta S is negative. So that means that delta G will be negative or spontaneous at low temperatures. We can also go through a similar process that we did before. So for instance, we could write out delta G is equal to delta H minus T delta S. And then we could look at the magnitude of delta H versus delta S. So in this case, delta H is negative, delta S is negative. So that means that T delta S is actually positive. So then if delta H is greater than T delta S, that means that delta G will be negative because delta H is negative and it's larger than T delta S. And if delta H is greater than T delta S, that tells us that temperature is pretty low because T delta S is low. All right, so that tells us that this process is spontaneous at low temperatures. Okay, so let's look at B. So in part B, we have CO2 as a solid, so that's dry ice, and it's becoming a gas. So it's undergoing sublimation. All right, so let's predict the signs of delta H and delta S. So let's start with delta H. If we're going from a solid to a gas, is that exothermic or endothermic? So it is endothermic, right? We need heat in order for a solid to turn into a gas. So if this is an endothermic process, is delta H positive or negative? Positive, right? Because it's taking in heat. So that's greater than 0. And now let's figure out delta S. So which state is more disordered, a solid or a gas? So the gas is more disordered, right? So if we're going towards more disorder, is entropy increasing or decreasing? It's increasing, right? So then is delta S positive or negative? Positive. So entropy is increasing. Okay, so if we look at our chart, we have a positive enthalpy and a positive entropy. So that's the last row. So this is a temperature dependent situation, and we're told in the chart that delta G will be negative, or the reaction will be spontaneous at high temperature. But we can also reason through this looking at our Gibbs free energy equation. So delta H is positive, delta S is positive, and that actually makes that whole thing, T delta S negative. Okay, so then again, we have opposing signs, so it depends on the temperature. So in this case, if delta H is greater in magnitude than T delta S, delta H is positive. So if it's overpowering T delta S, that means delta G will also be positive or non-spontaneous. Now, because delta H is greater than T delta S, that means temperature must be low. So that tells us that this reaction will be non-spontaneous at low temperatures. Now, if we consider the other instance where delta H is less in magnitude than T delta S, then that would tell us that T delta S is overpowering delta H. So the whole thing will become negative. So delta G will be less than 0. Now, if T delta S is much greater than delta H, that means that we have a high temperature because that's what's making T delta S so large. Okay, and that tells us that delta G is negative, or the reaction is spontaneous at high temperatures. Okay, so work through C and D, and then if you get stuck, you can always consult the worksheet key. But I think we're going to stop there this week, and next time we'll finish up chapter 18. We'll talk about other ways to calculate Gibbs free energy and entropy, and we'll talk about which situations to use which equations in. So if you do have any questions, just let me know. I'm available by email, or you can set up an office hour with me. And I will see you in the next video.